In this third lecture on Biot-Savart Law, today we shall continue our discussion on the application of law to the one-dimensional cases. Today we shall first consider a parabolic conductor. A parabola whose equation is y square is equal to 4ax carrying a current in anti-clockwise sense when looked down the positive z-axis, which is taken to the positive sense of circulation. Our aim is to find out the field at the focus which has a coordinate a0. So the source coordinate, if we consider this point to be Q, the source coordinate R prime is equal to OQ prime. OQ is equal to I cap x prime plus j cap y prime. Instead of writing this in terms of x and y, it is better to go to the parabolic representation. Basically, the curve has an equation which in this case is equal to y square is equal to 4ax. So amongst x and y, only one is independent and other one is determined by this relation. So it is better to deal with the parametric representation which this x and y values satisfies this equation for all t's. So this becomes I cap at square plus j cap 2at. So the differentiation or the length element is a taken common, I cap, so 2a taken common, I cap t plus j cap. Note that the dr prime, the incremental change on the source of the source coordinate is to the right as denoted by the arrow, and the current is flowing in the anti-clockwise sense. So when we shall use dr prime in the Biot-Savart law, a minus sign has to be added. The field coordinate R is OF, and this is simply I cap A. And so we need to calculate relative coordinate R is equal to R minus R prime. This is QF. This in our case is I cap A 1 minus t square minus 2i j cap minus j cap twice at, and the magnitude of R is this square plus this square square rooted. This is the magnitude of R. So the field at B at F, the induction at F is equal to mu 0 I times 4 pi minus dr prime, the minus sign has been explained, cross R by R cube. This is equal to minus mu 0 I upon 4 pi. For dr prime, I write this expression. There is t dt. The differential is over t, so this t is there. 2a I cap t plus j cap dt cross capital R I cap a 1 minus t square minus j cap 2at a cube 1 plus t square cube. This is for R. So this, there is a over here and there is a in both the terms. So a taken common. So this makes it 1 by a, and these two makes 2 pi a and the dt by 1 plus t square whole cube, and the rest part is the vector part. Two has been taken care of, this has been taken care of, so this is t plus 1, and here a has been taken care of, so this is 1 minus t square minus 2t. Clearly it will have only the z component, and the z component will have a minus sign, both the term will be negative, which adjusts with this negative sign. So this is plus k cap mu 0 I upon 2 pi a the vector part is this 2 minus 2t square, so this makes the 1 plus t square. So this here is a cube, so the result is the final result is k cap mu 0 I 2 pi a dt. This is the field at F due to this current element. The field is always directed towards us, towards the viewer. So the total field is integrated, is obtained by integrating this. So the total field B at F is obtained by integrating dVf from minus infinity to plus infinity. So this is k cap mu 0 I upon 2 pi a minus infinity to plus infinity since the integrand is even, we replace it by 2 and the result is mu 0 I by pi a dt 1 plus t square whole square 0 to infinity. Now the fact remains to calculate the integration. We write j as we write for t sec theta, so the result is t is written as tan theta, so this is sec square theta d theta, and the denominator is tan to sec to the power one plus six to the power 2 theta. The limit is when t is equal to 0, theta is 0, and when t is infinity, theta is pi by 2. So the result is sec square theta, so this result is cos square theta d theta from 0 to pi, which we write as 1 upon cos 2 theta d theta from 0 to pi. It will give you sin theta, which when integrated with the limits gives you 0, so the result is pi by 2. So the total field is simply k cap mu 0 I upon 2a, which is the field at the focus of the parabolic wave. With this example, we then go for the fields at the at the centroid of an isosceles triangle. We have a triangle of equal size carrying a current I. The triangle is ABC and the centroid is over here G. Our aim is to calculate the field at G. Obviously, if we calculate the field at G, the field will be directed towards us. And we know that if we have a conductor of finite length, and if this perpendicular distance be D, and these are the angle minus theta 1 and this is minus theta 2, then the field is obtained as mu 0 I upon 4 pi d theta 2 plus theta 1. This is the field, and the direction is, in this case, if we consider the triangle to lie in xy plane and the circulation of current in anti-clockwise sense, then it is along k cap. So for this this is the d, distance d, and this angle is 60 degree, this angle is 30, so this angle is 60 degree. So the field due to the side AB is k cap times mu 0 I by 4 pi 4 pi d times 2 into sine 60 degree, because this angle is 60 degree, this angle is 60 degree, two contributions, they are of equal amount, so this is 2 sine. This is the field due to the side AB, and the field at G is 3 times BAB, so this is k cap mu 0 I by 4 pi d 6 sine 60 degree. If we consider in a square, if we consider a square and we find what is the field at the center where the two diagonals meets, then if this is be the distance d, then the field at G or G will be BAB, the field due to this when it carries current in this sense is k cap mu 0 I upon 4 pi d. This time this angle is 45 degree, so this is 2 times sine 45 degree, and total field is obtained by multiplying this by 4. This type of calculation of regular geometry can be continued to a n-sided regular polygon. Let us come to an n-sided regular polygon. So n-sided regular polygon. The polygon is like this. And which carries a current. This is A, B, C, D, E, and so on and so forth. This is the regular polygon. And the distance we consider a point within it, so that each distance is d. This D must not be confused with the point D. This is the distance D. If we consider the side AB, then this AB side, when drawn in an extended way, this is the distance D, and this is the angle that they make. This is theta n, this is theta n. So total angle subtended over here is the sum, each side subtends 2 theta n, this is 2 theta n. So the total angle subtended is 2 theta n times n is equal to 2 pi, or theta n is equal to pi by n. So if we consider what is the contribution of the field at this point due to side AB, this is k cap. If we consider the polygon to be in xy plane and the current is flowing in the anti-clockwise sense, then it is mu 0 I upon 4 pi d, d is this distance, into 2 sine of theta n. This 2 cancels with this. Sine pi by n. So what is the total field? Total field at point O is the sum of n sides. So this should not be crossed. So this is k cap mu 0 I upon 2 pi d n times sine pi by n. If we consider a polygon, regular polygon of whose sides n increases indefinitely, then the polygon and the side of and this each side becomes vanishingly small, then the polygon approximates to a circle, and d becomes the radius of the circle. So these are the regular polygons. If n is sufficiently high, the polygon approximates the circle in a nice way. So what we know, if n tends to infinity, then the circle can be adequately represented by the regular polygon, and this result with n tends to infinity must corroborate with the result obtained for the field at the center of a circular conductor. To this end, we rewrite this expression as this pi and this O. And in the limit n tends to infinity, this argument goes to 0, and this goes to n tends to infinity, this goes to kg. This is indeed the field at the center of a circle carrying a current I and radius r. Now we should consider another case where we want to find out the field at an axial point due to a square loop of curve, square loop. So the geometry is this. Field on the axis axis of a square loop. We consider a square loop of length L carrying a current I. Our aim is to find out a field at a point which is at a distance z above the central z above. So this is a square loop and this is the same two diagonal meeting point of the diagonal, and we want to find out a field which is at a distance z from the center of the square and the axis in a direction perpendicular to the plane of the square. So we assume that the square lies in xy plane and this is the center. So the field that has to be found out is on the z axis, and when we look down the z axis, the current flows in anti-clockwise sense. So with this, the geometry becomes this. This is the square loop A, B, C, D. This is the square loop. It carries a current I. Each side is L, and this is the center. This is y axis. This is x axis. This is our z axis, and the field is to be found out at P having the coordinate 0, 0, z. And the current we consider a source point here. So this is the coordinate r prime. This is capital R. This is R. So for this, the field point has the coordinate OP. R is equal to OP. As per our choice, this is k cap z. And if we consider the length element, consider the arm, thus the r prime for the side AB, r prime is equal to this length. You see that x is constant on AB, x is constant at L, so this is I cap L plus j cap y prime. So immediately what we get, dr prime is equal to j cap dy prime, and capital R, the relative coordinate, is equal to r minus r prime is equal to minus I cap L minus j cap y prime plus k cap z. If we want to find out the magnitude of R, this is L square plus z square plus y prime squared to the square, which we call it as y prime square plus x square to the power root, where x square is been introduced as L square plus z square. Now the field at P due to the side AB is of the first, the field at P due to this current element is DAB is equal to mu 0 I upon 4 pi, then dr prime cross R by r cube. This is equal to mu 0 I upon 4 pi For dr prime I write this j dy prime cross. For capital R this is minus I cap L minus j cap y prime plus k cap z. Y prime square plus a square to the power 3 by 2. Now if we perform this dot cross product j cross I, j cross I is minus k and there is another k, so this is L times k cap, and if we cross j cross k this is I cap, so this is I cap z. You note that only the term in the denominator has y dependence, everything else is independent of y. So if we want to find out the total field at P due to the intersection AB, so this would be BAB is the integration of this actually we have considered a square of length 12. So this becomes, since the integrand is even, this will be just a 2 times mu 0 I times 2 pi mu 0 I times 2 pi, this 2 cancels with this, k cap L plus I cap z integration dy prime positive dy prime y prime square plus a square to the power 3 by 2 from 0 to L. Now this integration can be evaluated. We call it j, the indefinite part is called j, so if we call it j, then j integration is dy prime by we use the substitution y prime is equal to a tan theta, so that the denominator is a cube sec cube theta and the numerator is a sec square theta d theta, so the result becomes 1 by a square cos theta d theta, this is sin theta by a square. Now we use the substitution y prime is equal to a tan theta, so that tan theta is equal to y prime by a, so that sin theta is y prime by a square plus y prime square root. Keeping the mind that value of a is this, we come to the conclusion that it is 1 by a square times y prime by a square plus y prime square root. This is the with proper limits. So if we want to replace this marked part, this will be within the limits L to 0. The 0 part doesn't contribute, so the L part contributes. So the field is this part is mu 0 upon 2 pi k cap L plus I cap Z times this quantity. So in the numerator we will have L, and in the denominator we will have a square. For a square we write L square plus Z square, and for this part we write already it is L square plus Z square, and another L square will add, so this is Z square plus 2L square. This is the field. So let me write it clearly, 2L square. This is the field. If we consider the side CD, the contribution to the field arising from the side CD, this part will be negative. So this term will go, and when added, this will be this k component will be multiplied by 2. Or similarly, if we consider that these two sides, the field will have one k component, the z component is like this, and the y component will have the variation plus minus j cap z, which this side and this side, when added, this part goes. So the total field at P is simply the 4 times the z component of this field. So that we write that total field B at P is equal to 4 times, this is mu 0 I upon 4 pi, mu 0 I upon 2 pi, this from k cap, the vector direction is k cap, there is one L, there is another L, so numerator will be L square, and in the denominator we will have L square plus Z square square root of Z square plus 2L square. This is the total field at P. If we consider that Z is very large, in that case one can replace or neglect L square in presence of Z square, and the field for Z much greater than L becomes twice mu 0 I by pi L square Z cube. This is a dipole field, dipolar field. And we shall see later on, if we consider a point far away from this closed current carrying loop, then it behaves as a magnetic dipole whose dipole moment is the current, circulating current times the area. That is, the dipole moment will be L square times k cap I. This is the dipole moment. We shall come to the dipole moment in a later class. So this is the field which is produced at the point, at an axial point. By this we end our discussion on the application of Biot-Savart law to one-dimensional conductor. In the next lecture we shall consider two-dimensional conductor and apply Biot-Savart law to a plain sheet having uniform surface density of charge and a solenoid to calculate will be considered for the calculation of magnetic field.